Hello, everyone. We thank you for joining us today, whether it's morning, afternoon, evening for those. We do appreciate you taking the time out of your day to attend the webinar here. My name is Jordan Bellinor. I will be the moderator for today's session. We will be discussing bringing engineering on board and resetting IT, and this will be led by Andrew Ginter, Waterfall's VP of Industrial Security. A couple notes before we do kick off here. Recording is in session right now. We will be sharing an email following the wrapping up of this, and that should be expected to be out to you in the next couple of days here. We are also having a question and answer session. Please feel free, as Andrew's speaking, to upload any of those in the Q&A panel. And we'll make sure that we're spending some time towards the end to make sure that we can go through all that. If we do not get to all the questions, please rest assured Andrew and the team will be following up individually to make sure that we can share some responses with you. With that, I will stop. I'll pass it off to Andrew.
Okay, thank you, Jordan. We have IT teams, we have OT teams, we have people responsible for cybersecurity in our physical operations. These people work for the same company, they have the same goals, but very often we don't get along. The CISO is given responsibility for OT cybersecurity. The CEO says engineering hasn't been doing the job we think they need to be doing. You're responsible now. The CISO sends his people into the plant, the power plant, the factory, and they look around and they say, "What do you mean you haven't installed security updates in a year? What do you mean there's no antivirus on these machines? Fix this." You know, and it begins. It's as if they need relationship counseling. So, what do we do about this? And I'm going to go off video for a moment here because I want the internet to focus on getting my voice across to you. Here we go. To me, the correct response from engineering is not, what do you mean? The correct response is a simple question saying, I will be happy, I will be delighted to patch everything the moment you can tell me how likely that is to kill anyone. To which the typical response from IT is, what? And we have to explain. This is, the moment you get asked a question, you have an opportunity to learn. And so we have an opportunity to explain consequence. Consequence is the difference between IT and OT networks. What's the very worst that can happen on an IT network? We leak personally identifiable information into the internet. The bad guys steal it. We shut down order processing for a couple of days because it's all encrypted. What do we do when we suffer those losses? We take forensic images. We isolate the affected equipment, take forensic images, erase them, restore from backups, and come back online. This is the essential difference between IT and OT. What's the worst that can happen on OT? Things blow up, people die. Oh, the essential difference is that we can't restore human lives and damaged equipment from backups. This is why, for high consequence OT sites, we have this thing called engineering change control. This is the methodology that engineers use to control certain kinds of risks. Whenever we make a change to a system, there's a risk of making a mistake, errors and omissions. And there's a risk that those mistakes will cause a safety incident, will cause things to blow up and kill people. And so when engineers are dealing with large, powerful, dangerous physical processes, they study change. They study any kind of change that might cause things to blow up and die. They test those changes, they design them carefully, they control change to control risk. What's a security update? It's a massive change. How much software changed? We don't know. The vendor didn't tell us. How likely is that change to kill anyone? Well, we don't have the source code. And bluntly, even if we did have the source code, we probably wouldn't understand it. 9 times out of 10, the vendor barely, the vendor's people barely understand it. And so what do? We have to test this stuff at length before we trust it on our critical processes. And even when we've tested the thing, when we figured out that there is no material impact on safety, we have to ask the question, right? So next question, we've got $1 billion physical process. How likely is this change to cause an unplanned shutdown of the $1 billion process and cost us who knows how many millions of dollars per hour of lost production, of lost service to the community, of losses? Again, engineering change control to control these risks. Not a lot, important parts of IT security programs look like constant aggressive change to stay ahead of the bad guys. The exact opposite of what we need in terms of engineering change control. So the defining difference between IT and OT is consequence. One of the ways that engineers manage consequence on OT networks is change control, which flies in the face of commonplace IT practice. Eventually, and it doesn't take that long, okay, these people are smart people, sooner than later, they figure out, okay, I get it. Some of these systems are special. We can't patch them promptly at all. We can't antivirus them. We can't encrypt them. We can't find. The fact that we cannot do this does not make the threat go away. How are you going to address the threat? To which the typical engineering response is, what? I thought you had that covered. Okay, there's a widespread impression among a lot of engineering teams that cybersecurity is IT's job. IT has solved the problem. Engineering can ignore it. This is IT's opportunity to come back and explain how attacks work, explain how defenses work, explain what defenses they've deployed, and explain what are the limitations of their defenses. What is the residual risk? How can this attack or that attack, bang, 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 get through the defenses and put OT at risk? What a lot of engineering teams don't understand, what to a degree some IT teams don't understand, is that you defend IT networks very differently than you defend OT networks. IT networks are internet exposed. We need to be able to read email from our laptops on the IT network. We need to be able to send email. We need to be able to browse the internet. These are functions that we have to support. So we defend our IT network in such a way as to enable those functions with reasonable defenses, given the consequences we might suffer. The consequences on IT networks, don't minimize them. The whole mess, ransomware, isolate, image, erase, restore, continue, might cost tens of millions of dollars. We might have to buy identity fraud insurance for everybody whose information we've leaked. These costs are undesirable. They might be material. We might have to report them to our shareholders, but they're generally acceptable. Generally, we can buy insurance for them. The insurer will accept the risk if we pay the premium. These are acceptable risks. And so we defend the IT network, understanding that what we're up against is acceptable consequences. On a lot of OT networks, the worst case consequence of compromise are unacceptable. And so the degree to which we defend IT networks is not sufficient for defending OT networks. Relying on IT defenses on the IT network to keep the bad guys out of OT is a serious mistake, because we need to defend OT much more thoroughly. So now, IT gets it. we have a problem. We cannot use the normal protections. Um, OT gets it. Engineering gets it. We have a problem. We're not adequately defended. What are we going to do about this? And we start looking at protections. And when we start looking at this, there's a second fundamental difference. Okay, the defining difference between the two is consequence. There's a second difference, and that is espionage versus sabotage. Um, in an IT network, what is the asset we're protecting? It is information. We protect the confidentiality, integrity, availability of information, or mix up the priorities of it. We protect information. Information is the asset. In OT, what's the asset? It's the billion-dollar, the multi-billion-dollar physical operation. Okay, the gasoline pipeline, the power plant, the automobile manufacturing factory that we built at a cost of $2 billion, and it produces $3 billion worth of automobiles per year. The goal in terms of protecting physical operations is to assure safe, reliable, and efficient physical operations, not to protect the information. This is, a fundamental difference. It's not the defining difference, but it is a difference. And you look at the evolution of OT security advice. We've only been at this game in 20 years plus a couple, maybe, depends on how you count it. In 20 years, we've been through 3 generations of advice. The first generation of advice that came out right after the 9/11 attack on the World Trade Center, not a cyber attack, but it was an attack that caused people to start asking questions. That atrocity was a failure of imagination. We never imagined people could use commercial aircraft as weapons. What else have we failed to imagine? And they came around to OT security. And this is where the OT security stuff got started. When it got started in the early 2000s, who did we call on? There were practically no OT security experts in the world. Nobody was doing this. And so we called on the experts, IT security. A bunch of them came over and helped us out. Thank you for that. And so, in a sense, it's not surprising. The first generation of OT security advice looked a lot like IT security advice. It said, patch everything. I know it's hard. Try anyway. Do the best you can. You put antivirus everywhere. I know it's hard. Do the best you can. Encrypt everything. Authenticate everything. I know it's hard. Do the best you can. And if you cannot do the right thing, well, then, I don't know, put some compensating measures in place. Try to address the threat another way. So the first generation of OT security advice said information is the asset. Protect the integrity, availability, blah, 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 of the information. Do it with all the usual IT security tools. I know they're hard to use. Try harder. And if you can't do it, do something else. And it was better than nothing. Thank you for that. After a couple of years of using the advice, the engineers looked around and said, this is better than nothing. Thank you. But what we have here is a physical asset, not an information asset. We need to assure safe, reliable, efficient operations. And what we're preventing primarily, not universally, but primarily, is sabotage. What is the big threat? The thing that most IT, enterprise security teams are focused on? It is espionage. It is theft of information, theft of personally identifiable information, theft of other intellectual property. Espionage. The risk that most of us care first about on OT networks is preventing sabotage. Stop things from blowing up and killing people. Here's the thing. 50-year-old cybersecurity theory points out the difference between how you prevent espionage versus how you prevent sabotage. This is research that was done in the mid-1970s for the American military. The seminal paper is by Bell and uh, the other person, Lapadula. And they point out that if you've got a classified information repository and you've got lower classification people who aren't allowed to see that on another network or another part of the mainframe, you must prevent the low security people from reading from the high security, and you must prevent the high security from writing to the low security. Why? Well, because if malware gets into the high security part of it and it starts writing national secrets to the low security area where any fool can read them, that's a problem. Oh, this is cybersecurity theory. We all learn this in our CISSP training. To prevent espionage, it's a different theory. It's not Bell Lapadula, it's Biba. 2 years later, Biba came out with a seminal paper saying if you want to prevent sabotage, you must prevent people writing. And what's the example? On a mainframe that has classified information, preventing espionage means preventing the bad guys from stealing the designs for nuclear weapons. Oh, big problem. That's right. This is the problem that is being solved by this theory. Espionage versus, sabotage. What's the sabotage example? It is preventing the bad guys from changing the targets for the nuclear bombs. Oh, that's important too. So to prevent changing the targets, we got to prevent writing from the low security enclave into a high security enclave, because you might write the wrong information. And you must prevent reading. You must prevent the high security enclave. You must prevent them from reading from the low security enclave, because what they read might be malware and they might trigger a change to a critical parameter. So with espionage, you can read down and you can write up. With sabotage, you can write down, but you must never read up. It's the opposite. You use a lot of the same cybersecurity tools, but you're looking at the problem a different way. You've got a different priority. So consequence defines the difference, but there's also an important difference in that most of the time we're trying to prevent sabotage versus espionage. And second gen advice came out realizing that. Now, they never used the word sabotage and espionage, but the second gen advice realized that all cyber sabotage is information by definition. That's the definition of cyber sabotage. All information flows can contain attack information. And so what we must do is prevent the flow. We must inventory our information flows into the critical system, and we must prevent attack information from entering the system. We have to control the flow of information into the system. This is a sort of the second gen perspective. The third gen perspective is upon us now. It's only a couple of years old. It's not done yet. The theory is not even there yet. It's more of a collection of practice. We don't have the mathematical theory for the third generation, but the third generation is all about resilience. What does that mean? Textbook example is if you're in a coal-fired power plant, you've got a large boiler, massive boiler. You are the technician responsible for the boiler. You work 8 hours a day within the kill radius of a worst case boiler explosion. How would you like to be protected from a cyber attack that overheats the furnace under all of your boilers at once? Would you prefer a mechanical valve where if the pressure becomes too great, the steam forces a piece of steel against a spring, the steam escapes and there's no explosion? Or would you prefer a longer password on the computer controlling the furnaces? This is the thing. Most people would prefer the mechanical valve. It's unhackable. They'd prefer a few of these valves in parallel so that if one of them fails due to corrosion or metal fatigue, the other will save our lives. Cyber-informed engineering is the big umbrella. All of cybersecurity fits under cyber-informed engineering, but also elements of safety engineering, protection engineering. Where is the overpressure valve in the NIST cybersecurity framework? No mention of it. Where is it in the industrial 62443 standard? No mention of it. These are cybersecurity standards. The pressure relief valve is part of safety engineering. So cyber-informed engineering is the big picture. It's all about resilience, and it's currently under development at Idaho National Laboratory. I recommend it to you. This is the most important change in perspective in OT security in 20 years. And it's all about, wherever feasible, using unhackable mitigations. What's engineering grade is what I call them. Deterministic, always behave the same way, with mathematically modelable failure rates. You can Google a bathtub curve. Engineering grade. What's the difference between engineering grade and IT grade? Well, imagine that we have a new design for bridges that has a lot of harmonic frequencies. People walking across the bridge start the wretched thing vibrating. People dancing on it. I'm sorry, the bridge is a goner. It's gonna disintegrate because of these frequencies. Just keep building up. Google Tacoma Narrows if you want to see an example of a bridge tearing itself apart because of harmonic frequencies. And so imagine that the design engineers for the bridge have designed in active dampers, multiply redundant hydraulics, multiply redundant control systems, multiply redundant AI controlling, the dampers. The bridge feels rock solid. How happy would you be driving across the bridge every day if you knew that the design engineer for the bridge hoped that if a cyber attack targeted the control system, hoped that we could detect the attack before it destroyed the bridge? How happy would you be driving across our bridge every day if you knew that the design engineer hoped that if we detected the attack, we could scramble an incident response team fast enough to prevent disaster? Hope is not what we expect of design engineers. We expect bridges to carry a specified load in a specified operating environment for a specified number of decades with a large margin for error. That's what we expect. Increasingly, when we design automation systems, what cyber-informed engineering teaches us is that we, as designers of dangerous automation systems, we are expected to design systems to carry a specified threat load until at least the next opportunity to upgrade. And we all know these opportunities come at long intervals in change-controlled environments with a large margin for error, because we might have misunderstood the threat, because we might have misestimated when is our next opportunity to upgrade. This is increasingly the expectation. This is the third generation of advice that's upon us. This is the guidance that I recommend to you to rely on when we together, IT and OT, are designing cybersecurity programs. Having established that we need to do things differently, we often degenerate into an argument over, well, who's going to do it? Who's in charge? What do I recommend? I recommend that, to a degree, this is the wrong question. Who's in charge is something for the organization to figure out. It's something for the management team to figure out. It's a people problem. It's not the technical problem that we need to solve here. I suggest it matters less who does the work than that the work gets done in the right way. Okay. We need to manage IT assets, internet exposed assets, aggressively, patch everything, encrypt everything. We need to do the usual enterprise security stuff on assets that are exposed to the internet. We need to manage safety critical and reliability critical assets as if, with the engineering change control discipline. Common wisdom out there is that, look, IT needs to learn that some OT systems are special. We cannot manage OT systems, some OT systems, the special ones. We cannot manage change controlled systems the way we manage the IT network. And engineering needs to learn that not all of our systems are special. For example, remote access. We have a machine that is connected to the internet on one side with a VPN or whatnot, and to the OT network on the other side. This is an internet exposed device. it had better not have known vulnerabilities. We really want it not to have unknown vulnerabilities. We need to lock this thing down 9 ways to Sunday. I don't care if it's an IT asset or an OT asset. We need to manage it aggressively. It's not a safety critical asset. Okay, remote access is a convenience. If remote access is essential to safety, if internet exposed remote access is essential to safety, we have a bad design. Okay, we need to fix that design on an emergency basis. So as long as we can agree on what is the right way to manage these assets, what's the right training people have to manage these assets, what's the right experience people have to manage each of these assets the right way, that's the important question, not who's going to manage it. Manage it, who is less important than how. With all that said, even with the best of intentions, we often make mistakes. And so, common mistakes to be aware of is, again, inertia. We might be used to managing everything on the OT network using change control because that way we don't make mistakes as to change controlling one and not the other. Well, you can't change control the remote access system. You shouldn't be change controlling anything that's exposed to the IT network where internet attacks can get in, or worse, exposed directly to the internet. So again, not all systems are special. Criticality. IT teams, once they learn about the safety imperative, often assume that on every OT network, the worst that can happen is people die and things blow up. Not true. Talk to the safety engineers. If there's enough overpressure relief and other electromechanical safeties in place, it may be physically impossible to bring about, or practically impossible to bring about, those consequences with a cyber attack, in which case we don't need to worry about safety as a consequence. The other is true as well. If IT goes in there and says the worst that will happen is people steal, I don't know, the programs off of our robots and sell them to our competitor, that's a problem. If in fact the worst that can happen is the bad guys get in and destroy our robots, and now the factory's down for 6 months, we need to talk to each other. Okay, the IT team brings a knowledge of attacks to the table, saying here's what's possible attack-wise. The engineers bring to the table, a knowledge of how they've designed the physical system to prevent damage to equipment, to prevent loss of life, so that they can compare notes and say, what is a credible threat? What is a credible consequence? We don't design our systems to deal with the worst case consequence. We design our systems to address the worst credible consequence. And we need conversation to make that happen. I've talked about damaged equipment as a risk a lot of people are blind to. Think about that, not just unplanned shutdowns. Think about destroying the equipment. Think about destroying the automation. How many of our factories are using 10-year-old PLCs? Fair number of them. What if the bad guys get in there and erase the firmware on 80% of our PLCs so thoroughly that we cannot recover the PLCs? They just won't boot. They won't boot far enough that we could load the new firmware. We have to throw them out. It's called bricking the stuff. If you brick 80% of the PLCs, how are you going to start the factory again? You might have backups of the PLC programs. So where are you going to buy 800 PLCs that the vendor doesn't make anymore? You're going to go on eBay? How many do we have in spare? Maybe 10%, maybe 20%. These things wear out. We need spares. So these are all potential blind spots. We need a lot of people in the room. We need a lot of knowledge in the room to cover all of these blind spots. Okay, what do we do? Once we've identified the blind spots, we've understood the problem, what do we do? Well, for the smallest sites, what I recommend we do is buy insurance, or at least get a quote. Get a quote. Why? Because the insurance company, as part of the quote, is going to give you a questionnaire, and you're going to say, yes, I do this. No, I don't do that, because they're going to try and assess the risk. Buy insurance. Do what the insurance company needs you to do to, secure the policy, to get the policy. Fill out the questionnaire. Fill it out cautiously. understate what you do. Okay, your goal is not to answer yes to every question and minimize the cost of the policy. Your goal is to, answer truthfully and answer cautiously, answer a little bit less than the security measures we actually have in place to maximize the likelihood of a payout if you suffer a loss. Because if we say yes, 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 we do all this stuff and we suffer a $10 million loss, you can be certain the insurance company will send an investigator in and say, you don't do these things. You've never done these things. We're not paying. And now we're out. So when the worst case consequences of compromise are acceptable by insurance. If you get a quote from the insurance company saying your worst case consequence is, $400 million, we say, yes, we'd like to cover a $400 million loss. And they say, and a mass casualty event. We say, yeah, we want insurance for that. They might give you a quote that is like $300 million a year, but it's only a $400 million policy. What they're telling you is that they're unwilling to accept the risk. The risk is too great. We have to do something else. This is where cyber-informed engineering comes in. It says, if we cannot transfer the risk, we have to reduce the risk. If we cannot reduce the risk using cybersecurity, the tools the insurance industry is familiar with, we have to do something else. We have to design our systems differently to eliminate the risk. When we're doing that design, don't be surprised if the first thing the engineering team comes back at you with is network segmentation. This is not a compensating measure. This is essential. Remember, cyber sabotage is information. Control the flow of information to control the risk. How do we control the flow of information? Well, the biggest flows of information are online. They're across networks. And so network segmentation is where we start, but controlling the flow of attack information. It's not a compensating measure. It's the first thing we go to. The first standard that came out of the 62443 series, that is, now the most detailed, the most widely used industrial security standard in the world. The first standard that came out was 1-1 that talked about concepts and terminology, and half of that standard was talking about segmentation. This is where it all starts. The latest advice that came out was this month. Google Secure Connectivity Principles for Operational Technology. It is something that came out from the UK, the National Cybersecurity Center in the UK, countersigned, approved by CISA, the Australian NCSC, the Canadian CCCS, and many others. There's this widespread consensus among government authorities saying this is the right way to do OT security. It all starts with network segmentation. Oh, what's the first thing you do? It said, on an emergency basis, find your internet exposed stuff and take the passwordless HMIs off the internet, people. Take your passwordless PLCs off the internet, and then we can talk about everything else. One of the things it says is move your IT gear, separate your IT and OT networks. Now, when you separate those networks, most people assume, hey, I'm going to create an OT network that's really secure. I'm going to move all my stuff to the OT network. You're going to have a shutdown to do that. We don't want to shut down. No. If you've got a mixed network, take your IT assets and move them into a new IT network. Leave the old OT network alone. Yes, make it more secure over time, but the first thing you do is get the IT assets off of it so that we can secure the OT network without shutting it down. Oh, inventory your data flows. Again, cyber sabotage is about the flow of information. Don't just inventory your equipment and say, I have to understand what I'm protecting in order to protect it. You cannot control information flows until you know what they are. Inventory your information flows as part of this segmentation and address dependencies. We've moved the let's call it, I don't know, the Maersk shipping example, not Petya. The container tracking system was crippled, was on the IT network. We moved the container tracking system from the OT network into the IT network. There, now we've separated the two. And when container tracking goes down, everything stops. It doesn't matter how secure our OT network is if we depend on an IT asset. Identify those dependencies and figure out what we're going to do about them. So, and the advice says when you've got high consequence stuff on the OT network, and most of the time we do, Segmentation is fundamental, and hardware enforced segmentation is preferable. And they've got several sections talking about hardware enforced segmentation. What is the most common example? Most common example of hardware enforced segmentation is the unidirectional gateway. The NIST 882 standard defines a gateway as a combination of hardware and software. The hardware is physically able to send information in only one direction, and the software makes copies of servers. What does that mean? Well, if you take the waterfall version of this and you look under the hood, there's a physical divider down the center of the unit. You can run your finger, an auditor can run their finger down the divider and verify visually that there is no cross connect inside the unit. Really, this is two units in one. And on the left side, there's a fiber optic transmitter. On the right side, there's a fiber optic receiver. The only cross connect, okay, not even power is cross connected inside the unit. The only cross connect is a single fiber optic cable on the front of the unit. You can send information from the high security to the low. You can write from high to low in BIBA's terminology. You cannot write from low to high. Why? Because there is no laser in the receiving circuit board. It's not physically possible to send attack information into the network through this device. This is what the latest advice from all of these agencies recommends. Oh, and the software, for the record, makes copies of stuff so that it's a plug-and-play replacement for the IT/OT firewall. The software, if we have an Oracle server, if we have an OPC server that has all of the data in it that we've carefully gathered from our thousands of OT devices, and we want to make available to the IT network, the software logs in. It's more complicated than this, but let's say back of the envelope, logs in once a second and says, give me everything new. OPC, all the tags and all the values. Oracle, everything with a timestamp since a second ago when I logged in last, gets a few megabytes of data, pushes the data through the weird hardware. Nothing else sees the hardware. It's only the gateway software sees that weird hardware. And on the other side, inserts the data into an identical server. So now we have an OPC server or an Oracle server or an enterprise Pi server on the enterprise network. Anybody who needs the data can ask the enterprise server for the data, gets the same answer as the live server would have given. No writing back into OT, not even a question saying, please give me the data. Nothing gets back. This is the theory. And this is the principle. If you look at Bell LaPadula, if you look at BIBA, they recognize that the principle cannot always be universally applied. There is going to be leakage out of classified networks. You have to send information out of them sometimes. There is going to be leakage into safety critical networks. You're going to have to send information into there from time to time. What do you do with that? You scrutinize that stuff 9 ways to Sunday. And the segmentation advice tells you to do that. One of the things the segmentation advice calls out is remote access. If you want remote access into the OT network, that's information entering the OT network, isn't it? And so the January advice echoes what came out about 2 years ago, again, from CISA and CCCS and the New Zealand authorities, echoes the advice saying, yeah, on IT networks, please, please, please stop using VPNs. Okay, they have vulnerabilities. They have 0 days. They're going to get compromised. Please stop using jump hosts. It's all software. On high consequence networks, I need you to use hardware enforced protection. Ideally, hardware enforced remote access. This is recommended in this month's advice. It's recommended in the 2-year-old remote access device. Google modern approaches to network access security. What is hardware enforced remote access? Well, here's one example. You've got a remote laptop. Think in a hotel room. You've got an intervening network. Think, the IT network or the internet. You've got an access point. In this case, a HERA gateway. What's HERA? Hardware enforced remote access. It consists of 2 cooperating unidirectional gateways. One is sending information out of the OT network. The other is sending information in to the OT network. It's sending encrypted keystroke and mouse in, and it's sending encrypted screen images out. Yeah, that's what software does. Why is this more stronger than software? Well, think about it. Each of the gateways, if you remember the diagram, this diagram, there's 2 CPUs in each gateway, one on the inside, one on the outside, physically divided. Each of the gateways has 2 CPUs. The cooperating set of gateways has 4 CPUs, 2 on the inside and 2 on the outside. 2 on the IT network, 2 on the internet, 2 on the OT network. Imagine the bad guys have found a 0-day in the CPUs facing the internet. Imagine that they utterly taken over those 2 CPUs, but what they want to do is not take over the gateway and deny service. That's just annoying. What they want to do is break into OT and work their will upon the physical process, damage equipment, cause things to blow up, whatever. So they've taken over these CPUs. They say, I'm going to use the compromised CPUs. I'm going to pivot. I'm going to use the compromised CPUs in this device to attack deeper into the network. Well, look at the bottom device. It's one way out, screen images, nothing back. The hardware cannot send anything back. This CPU is worthless. It cannot send attack information. It's physically impossible to send it into the OT network. That's fine, say the bad guys. We have the other CPU. The one on top is inbound, isn't it? And so they start using that CPU to launch SYN floods and to launch stolen passwords and to launch buffer overflow attacks into the OT network, and the hardware throws it all out. What? The bad guys are annoyed now. What do you mean the hardware throws it all out? The hardware throws it all out. The HERA, the HERA protocol is designed for hardware filtering. All it gets through is encrypted keystroke and mouse. Fine, say the bad guys. We'll do this the hard way. We will hijack a session. We will take those encrypted screen images. We will fake the encrypted keystroke and mouse. We will take over the OT side of this device so that we can work our will upon the OT network. And here's the thing: in order, the credentials for encrypting that keystroke and mouse, that lives in TPM hardware on the client, and it lives in TPM hardware on the inside CPU of the device here. This is hardware. They're designed to make those credentials practically impossible to steal. Worse, the bad guys, even if they found a vulnerability in the TPM, even if they found a way to steal the credentials, they would have to, break into the OT network to steal the credentials in order to fake the keystroke and mouse to break into the OT network. Okay, it's a chicken and egg problem. You got to break in to steal the credentials before you can break in to steal the credentials. And so it's not as simple a value proposition as unidirectional gateways, one way out, nothing back, any questions. But it's dramatically more secure than software. And this is why it's recommended by CISA and the NCCS and NCSC and all of these other authorities. So, what's the bottom line? HERA is something new in the world. The technology was only invented a couple of years ago. It introduces a hardware-enforced protocol break. You've got the HERA protocol on the outside, and you've got whatever's needed on the inside: remote desktop, VNC, SSH, whatever is the right way to access OT devices. The hardware, the TPM hardware, prevents forging keystroke and mouse. The protocol's designed for hardware filtering. Again, dramatically reduced attack surface. This is my last slide. Let's sum it up. Key learnings: once we can get IT and OT to cooperate, the problem's not solved. We need to solve the problem together. We need to recognize that IT grade security that we use on IT networks is not enough to protect most OT systems. This is often a surprise both to IT and OT. Segmentation is fundamental. It's not a compensating measure. This is how we prevent sabotage. We have to control the movement of attack information. We do that with segmentation. We do it with USB device controls. We prefer to use engineering grade protections. This is what CIE teaches us. Whenever practical, use engineering grade protections, unidirectional gateways, overpressure relief valves, to prevent truly unacceptable consequences. Trains collide, mass casualty event. Don't get me wrong. The segmentation advice that came out this month also recommends firewalls inside the OT network to control lateral movement if something gets in. Firewalls have a role on OT networks. They have a role on IT networks. It's at the consequence boundary, the connection between two networks with dramatically different worst case consequences of compromise, that we need to do something different. And don't get me wrong, in the bridge example, I positioned detect, respond, and recover as an IT style solution, but we still need it. Okay, no fool builds a critical system, a safety critical system, protects it 9 ways to Sunday, and then ignores it. You've got to watch what's happening in there. We need to understand what's happening there. If we do have something bad in there, we need to know about it. We need to scramble a response. I know it takes time. I know it's not as strong protection as preventing the attack getting in the first place, but it is an essential secondary capability. Okay. It's not a question of do we need it or not. It's a question of what do we do first. We need it all. Where's the priorities? It's a perspective on the problem. That's what I had for you. I am coming back for question and answer. Jordan, have we got any questions in the queue?
Hey Andrew, yes, we do have quite a few here. As mentioned, we'll try and work through all these folks, but anything that we don't get to, we will make sure that we do follow up with. One of the ones here is how can engineering techniques be addressed in business continuity plans, including disaster recovery and testing?
Say that again slowly. How can engineering techniques
Be addressed in business continuity plans, including
Yeah.
disaster recovery and testing?
I'm not sure I understand the question. The cyber informed engineering umbrella, it's a body of knowledge, includes elements of safety engineering, preventing unsafe outcomes from all causes, earthquakes, for fires at the site, and cyber attacks. Protection engineering is focused on preventing damage to equipment, mostly electrical equipment, from all causes, including lightning strikes and human error and cyber attacks. Business continuity planning is an essential part of engineering. It's an essential part of the NIST cybersecurity framework. It's part of the govern pillar of the cybersecurity framework. Especially for critical infrastructures, we need to keep the lights on. We need to keep clean drinking water in the taps. And so the engineering discipline, the engineering approach contributes to that. So does the cybersecurity approach. When we are looking at contingency planning, I don't know. Here, I'm not sure if this is what the question is, but here's an example. We have a lot of us don't use overpressure relief valves anymore. A lot of people have said, look, safety instrumented systems are cheaper than overpressure relief valves. We can detect their failure faster. We can repair them faster. They're more reliable than overpressure relief valves. We're using safety instrumented systems. They're triply redundant. Each system has 3 CPUs in it. We're good. Well, if you compromise the CPU and reprogram the safety system, you're reprogramming all 3 CPUs at the same time. Safety systems are, they have the reputation they do for reliability, for safety, because they're designed so that they fail independently. If smoke rises out of one of the CPUs, the other 2 carry on. This happens from time to time. Things wear out. Independence, though, means that the CPUs need to be powered on separate power supplies, coming off of separate battery backups, so that if there's a common mode failure, the power goes out. We don't lose all of our safeties at once. When we do this, when we apply this engineering principle, to business continuity, keep the plant running in a cyber attack that targets a safety system, the safety system must be independent. The redundancy of the safety system has to be independent in the face of the cyber attack. Most of the time, we ignore that. What we need is 2 different safety systems on 2 different networks in 2 different, two different kinds of security, so that an attack that hits one of them and takes it out is unlikely, very unlikely, to impair the other. So cyber independence is a new principle when we're looking at reliability and to a degree, business continuity. I don't think that's the question, but that's what sprung to mind in my limited understanding of the question. What else have you got for me?
What are three things that IT teams can do for OT that will help them build trust?
Um, I know what OT teams need the most. But you have to be really careful with IT coming in saying, let me help you do this. It works best if we can persuade the engineering teams to ask questions so that IT can answer them. But cyber informed engineering positions OT security as a coin with two sides. One side of the coin is engineering, overpressure relief valves, manual operations as a fallback, turn off the automation, operate the physical process manually. This is engineering. The other side of the coin, and this is the piece that IT teams need to learn about: engineering change control, safety critical systems, and the options that are available to address those risks without cyber. The other side of the coin is what engineering terms urgently need to learn. They need to learn, what are the attacks out there coming after us? This is something that IT understands. They live these threats every day. They can explain to engineering teams how these attacks work. When I came into this field from, what I did before was design middleware product, design control system product. When I came into the security field, I took some training and I was appalled. I learned how these attacks work. I'm going, oh, this is horrible. I'm going out and closing my bank accounts. Forget this. This is not, internet exposed. No, forget it. I'm stuffing my money under the mattress, and I was appalled. This is a learning that engineering teams need to have. It's not IT's problem. You can't delegate it to IT. IT has to explain to engineering how much trouble they're in. Let me explain to you, bang, 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 we're in, people die. That's unacceptable. They need to explain to engineering teams not just how the attacks work, but why they work. We have protections in place on the IT network, yet the bad guys get through. Why? Well, because the easy way to defeat an antivirus is write something new for which no signature exists. Oh, the easy way to defeat two-factor authentication is not very easy, but a way to defeat two-factor authentication is wait until the two-factor authentication system, until the vendor publishes a vulnerability with a proof of concept exploit. Use the proof of concept exploit against your target, get in before the target has a chance to upgrade and install the security update. The sophisticated way is to find a 0-day and break in without anybody knowing. Engineers look at this and they go, this is not the value prop I thought I was buying from IT. I thought they had the problem solved. So they need to learn these things so that they can talk intelligently to IT, and so that they start demanding better security. To me, this is what engineering most urgently needs to learn. But you can't just come in here and say, let me teach you about attacks. Okay, there's got to be a conversation that goes on before that. Teaching works best when the student asks questions, when IT asks questions about how does that safety stuff work? Well, now let me teach you. When engineering asks questions about how much trouble am I in? Now let me teach you. You've got to, the initial part is I don't know, maybe you have to butt heads for a little while so that you start asking the right question.
I think this is a good one to kind of build off of what you're speaking about right now. You've talked about network data flows. What advice for corporations considering amalgamating IT and OT services would you share?
Yeah, and this is happening in a lot of places. It's been happening slowly but steadily for, I kid you not, 20 years. So it is happening. And when you amalgamate, again, the critical feature of the amalgamation is to make sure that all of the equipment, the IT equipment and the OT equipment, is managed the right way. You've got to understand what is the equipment, how critical is it to safety, how critical is it to reliability, what's the risk of making a mistake when you're managing the equipment, what are the consequences of that risk. One of the consequences, one of the risks is that if you send people into an OT server room and they've been trained on the right way to do, a security update on the OT remote access system, and they walk over to the wrong console and it's got the same password, and they log in and do an upgrade and it blue screens, and now the whole plant goes down because it's the main data acquisition server that they've just taken down. It's not just that there might be a mistake in the update for the remote access system. It's that the people touching the equipment might make a mistake. So what's critical is that we manage the equipment, all of it, the right way. You can't, if you do change control on the IT firewall to the internet, and it takes you 9 months to install an update, that's the wrong way to manage that asset. Manage it the right way. Teach people enough so that we don't have mistakes with unacceptable consequences. As that to me, that's the key. Who's in charge? Who's the boss? These are all personnel issues. These are management issues. These are people issues. I have no single answer to that. It all depends on the people involved and their capabilities. The technical piece is managing the equipment.
I know we are getting to the top of the hour here, and we're running out a bit of time. Some of the folks will need to drop off. Again, please rest assured this recording will be shared with you. Any questions that have been shared in the queue, we will make sure that we respond individually for. There are a couple others, so for anybody that would like to stay a few extra minutes, we can have Andrew answer a few of them here.
And the recording will go out, so anybody who misses a question or an answer here, if you're interested, you can always fast forward to the end of the recording.
What are your thoughts on the unified namespace OT architecture approach, data transferring via a pub sub broker technology, transferring something like MQTT from OT to IT via single port that's open only on a public?
There's a few answers there. So we're talking MQTT, OT to IT. Single port means through a firewall. MQTT first. For anyone not familiar with it, this is emerging as a dominant, if not the dominant way to communicate between OT equipment and cloud services. So of course we need it. The cloud is coming. We may not, a lot of engineering teams don't believe the cloud is coming, but it's coming. We've been using the cloud for 20, 30 years. We've been using the cloud since before it was the cloud. What do you mean? Predictive maintenance. We've got a power plant full of steam turbines. Who's the world's expert on maintaining the turbines? It's the vendor. It's the people who built the turbines. It's the people who maintain the turbines. Right. So for 30 years, we've been pushing data out to them across the internet, even before the internet across T1 lines, weren't we? So that they could analyze the data and recommend optimal maintenance and save us millions of dollars a year. We don't do this for our health. We do it because it's worth millions, tens of millions of dollars a year on a large site to us. We've been connected out to the cloud forever. It's coming. MQTT, if it's not here in your organization already, it will be. So yes, we need to do that. Sending it through a firewall, sending it outbound through a firewall through a single port is better than, having no firewall. But what's the risk? There's a risk inherent in the MQTT protocol. It is bidirectional. It's possible to imagine. Now you have to look hard for the vulnerabilities, but it's possible to imagine an attack that sends attack information back through that bidirectional MQTT conversation. The data flow may be from high to low to the IT network to the cloud through that firewall. The data flow may be high to low, but the communications is back and forth, isn't it? So there's a risk of encoding attack information in that bidirectional MQTT protocol. What people don't realize is that the firewall itself at the IT/OT interface introduces risk. Now, the risk may be acceptable in a small shoe factory. It's probably unacceptable in a large power plant. Why? Well, because firewalls are software. There are ways to break firewalls. What's the easy way to break a firewall? Shoulder surface, someone enters the admin password. They leave, you enter the admin password and add a rule that says allow all. Now the firewall's a router. What's the high-tech way to break a firewall? Find a 0-day, okay, a defect in the firewall that the bad guys or the good guys have not yet figured out how to patch. You might say, well, 0 days, that's really sophisticated. There were, I think, I saw a statistic, 60 or 70 or 80 0 days exploited in the wild last year. A lot of them in perimeter protection devices like VPNs and two-factor authentication systems and firewalls. And so it's not so much, it's not the question was about MQTT. The question should be about, is the firewall safe? Why is it reasonable to protect a connection between a passenger rail switching system and the internet? Why is that reasonable to protect that through a firewall? It's not. Can you do that with the unidirectional hardware? Yes, of course. You can put a unidirectional gateway in there. It will be an MQTT client on the OT network. It'll be an MQTT broker on the IT network. It works. One way out, nothing back. You can put that between a switching system and the internet safely. To be fair, I gave an example where some fool walks into the server room and walks up to the wrong equipment and does the wrong thing to the wrong equipment. The truly paranoid, and I've seen this, the truly paranoid separate the gateway into two circuit boards. One goes in the OT room, server room. One goes in the IT server room. And the only connection between the IT and OT server rooms is that one fiber. So that if you're going to manage an IT device, you walk into the IT server room and you do your stuff. You don't have a key card that gets you into the OT server room, so that you can't mistakenly pull the wrong wire and connect the OT network directly to the internet. So all of this is possible. I've only got an hour here on the webinar, but if you're interested in protecting OT networks unidirectionally, give us a call. This is what we do. Waterfall, and I've forgotten about Waterfall slide. We do unidirectional. We sell technology, not advice. If you want advice, give me a call. I'll give you my best shot, no charge. We can have a conversation about what's possible. So that's a long answer to your short question. I hope it made sense.
I think we got another one here that kind of ties into the overall theme that you've been talking about, OT and IT working together. Should IT be involved in the conversation on safety management, digital systems OT is using? And then maybe an extension on that, how involved, what's the best way to be working together?
I suggest yes. Now, don't get me wrong. I'm not saying IT should be stirring safety engineering's pot. Safety engineering is about math. It's about probabilities. There's a discipline of safety engineering that IT doesn't do. It's a different job. But the value that IT can bring to the table is, I'm sorry, where in your networks are you putting the safety systems? And answer the question, are those systems independent from the perspective of a cyber attack? IT is the experts on cyber attacks. They've got the penetration testers on staff. Engineering doesn't have penetration testers on staff. Safety engineering doesn't have pen testers on staff. IT has attack gurus on staff. They need to come in and answer the question, do we have independence here? Or are we fooling ourselves And in fact, there's a way to take all of our safeties down with a single attack vector, a single. That is, and again, that's not doing the math on safety and how many redundants do we need. That is pointing out, and helping the engineers work through a new failure mode whose characteristics need to be incorporated into their safety planning.
And maybe one last one. I know we're getting to 10 minutes over here. What determines a threat being considered credible?
Um, so credible is a new word that's being used in the space of cybersecurity risk management. Likelihood is the word we've used in the past. Risk is likelihood times impact. Likelihood works when we have frequency data. It works when the attacks are random. When the problem with likelihood when we talk about sophisticated attacks is that sophisticated attacks are not random. Okay, an intelligence agency is going to target us. If they have orders to take us down, they're going to hit us and hit us again until they take us down or until they're given different orders. Okay, likelihood is a reasonable way to model opportunistic attacks, but it's a poor way to model sophisticated attacks. Likelihood assumes that when an attack hits us, malware hits us, Stuxnet hits us, the outcome of the attack is random. It's not. If a powerful enough attack hits us, we're going down. If the same attack hits the same target a second time, we're going down. There is a degree of randomness in intrusion detection, in the detect, respond, recover paradigm. There's a degree of, but randomness is the wrong model. So credibility is what people are starting to ask. And it's defined as what is reasonable to believe. When we have, when we, as designers of systems, make decisions about other people's safety, we have a legal obligation to make reasonable decisions. So, a credible attack is an attack that is reasonable to believe will hit us or someone like us within our planning period, within, the until we have the opportunity to upgrade our OT security system again. This is the topic of my new book. I'll have chapters on it. This was the topic of a webinar I gave most of a year ago. You can go to the Waterfall website, go to the OT Resource Center, click on webinars, scroll back, and you can find it. But let me just really quickly give you an example in terms of what is, credible. Maybe two examples. One is, look, I was raised in Brooks, Alberta. I live in Canada. Brooks is in the middle of nowhere. Okay, it's 15,000 people, literally in the middle of nowhere. It's well connected with highways. You can get on any one of those highways. You can drive in any direction at highway speed for an hour before you find a bigger town. This is a tiny place in the middle of nowhere. They serve the local farming community. They serve a little bit of oil and gas activity. Do the Russians have the ability, the resources, the capability to get a sleeper cell of 3 absolute cyber gurus and plant them in the workforce of the town of Brooks water treatment system? And after 3 years of that sleeper cell sitting on their hands, activate them and carry out a crippling attack on the water treatment system that damages the equipment so badly that the system is down for 60 days. Do the Russians have the ability to do that? Yeah. What'll it cost them? I don't know, a few $1 million. You don't get experts to sit on their hands in a circumstance where they could be arrested for nothing for 3 years. You're going to have to pay them $5-10 million to make this happen. Is that a credible threat? Is it reasonable to believe that the Russians would do that to Brooks, Alberta? I don't think that's a credible threat. What good would it do the Russians to take out the water treatment system in the middle of nowhere? Is that a credible threat for the city of Washington, D.C., home of the Pentagon? I think it is. So this is credibility. It's what is reasonable to believe. And, people ask about it. How do you use that concept? I maintain that it is part of our legal obligation to do reasonable things. I mean, imagine that we're running, I don't know, a refinery. We've secured a refinery. The bad guys get in and blow up a catalytic cracker and kill 6 people. What's going to happen? Well, the refinery shut down. We have to repair these things. And there's going to be an inquiry, probably a judicial inquiry. We might get charged with incompetent, negligent death or something like this. At some point, we're going to be on the witness stand as the designers of the security program. Is the judge going to ask us, did you do the minimum the law requires? Did you follow the regulation? Not the question the judge's going to ask us. The judge is going to, is not going to ask us, did you do the minimum the standard requires? 62443. Did you do the minimum? Were you compliant with the standard? That's not the question the judge will ask us. The judge will ask us questions reflecting our legal obligation. The judge will say, when you designed your security program, did you consider the kind of attack that killed these 6 people? If the answer is no, Your Honor, I didn't. Why not? Given that the attack happened. If the answer is yes, the next question is going to be, when you considered that attack, did you regard it as a credible threat? Did you regard it as reasonable to defend against? And if the answer is no, the question is going to be, explain to me why it was not a credible threat, given that, in hindsight, it occurred. If the answer is yes, Your Honor, we did deem it a credible threat, the question is going to be, then explain to me why the defenses you put in place were reasonable, given that they failed and 6 people died. We have a legal obligation when we make decisions about other people's safety. This is the engineering, the engineering profession knows this. Engineers are trained on this in their ethics classes. They have a legal obligation to make reasonable decisions when they're making decisions about other people's safety, or when they're making decisions about, critical national infrastructure, or when they're making decisions about large amounts of other people's money. Okay, the investment in a $3 billion factory. Credibility is what is reasonable to believe and why it's reasonable to believe that. And this is, when you use that word to talk about high-end risk, you can ask questions like, credible threat. Are there any credible attacks with unacceptable consequences that we do not defeat with a high degree of confidence? It's a really important question. You can't ask that question with the word likelihood. So the word is something that we're starting to see used in risk assessment, and especially in communicating the results of risk assessments to management, so that management can understand the scenario. We have a credible attack that we don't defeat, that is likely to kill 6 people. What are we going to do about that? Are we going to accept the risk? Are we going to increase the security budget to address the risk? Are we going to, bring in safety engineering and try and design the risk out of the system? This is an important question that you can only ask if you have the right words to ask the question. So that's what I had for you. I hope it's useful.
Oh, good. I know we are 15 minutes over. There's still quite a few questions here. To anything that we did not get an answer to on this webinar, please rest assured, as mentioned, we will respond individually to that, Andrew and team, and hope that we continue those conversations there. Andrew, before we hop off here, are there any last words from you?
No, just thank you for everyone for listening, and thank you, Jordan, for hosting this and making it happen.
Absolutely. Thank you again, everyone, on behalf of Waterfall. We really do appreciate you taking the time to join us today. Have a good rest of the day, evening, night, wherever you may be in the world. All right, we'll see you again next time.